Okay, let's dive into shear, moment, and deflection functions. So one of the nice things about using tables or even the free body diagram method, which we'll talk about briefly, is they have complete solutions for the reactions, the shears, the moments, the moment at any point, the max deflection, and the deflection at any point. And so when we're designing simple span beams with reasonably simple loading, which is frankly 90% of the time, we can use these simple equations to quickly get the max moment, max shear, and then size a member. So these tools become really effective. And if we have more complex loading, sometimes it's worth the effort, which takes very little effort, to simplify the loading. Maybe you are 5 or 10% higher in your moment shears, but it just makes for a really simple analysis. Okay, so first let's talk about the free body diagram method. First, just from a practical point of view, this would be kind of the corollary between reality and how we would model what's going on in this type of a building. So from these point loads from the double T's here, create loads on our beam, our concrete beam that we might design, and then from there we can do the analysis and find things out. Another thing to think about is often the shear and moment diagrams will influence the shape of a member. So here we have a girder sitting on this. The shear and moment in this area is less than where we have two sitting on the member. So the taper of this column cap actually makes sense because the shear is double in this area than it is right here. Anyway, so kind of keep, as you're driving about or traveling about, keep an eye out for the shape of the structures that you might be designing at some point and start to understand or ponder why are they that shape. Okay, so the free body diagram method, we're going to take our loaded beam, and in this case it's a triangular load, 3 kips per foot. We're going to reduce that load to a point load, which is at the centroid of the shape, which happens to be a third over from the fat end. So to get the 13.5 kips, we multiply 3 kips per foot times 9 feet divided by 2 because we're only half of a rectangle. Okay, with that, we can solve for the reactions. So sum of moments about here, sum of moments about here, sum of forces vertically gives us a check on our math. And then we take our member and cut it at point C because someone has decided that's where we're interested in finding the moments, shears, and axial forces. So we take that cut, so this is point C right here, and wherever we cut through the beam, we replace that with a shear, an axial force, so a force along the axis of the long axis of the member, and a moment. From here, we can solve this using our 3 degrees of freedom or our 3 equations of equilibrium in a two-dimensional space. So if I sum moments, if I sum moments about here, my shear and axial force drop out of the equation, so I can solve directly for that. If I then sum forces in the horizontal direction, I'll see quickly in this case that N sub C is 0 because there's no horizontal reaction or horizontal force anywhere in the system. And then if I sum forces vertically, I have a known force here, I have a known reaction here, and I can find my vertical force, shear force, at this point. And then I can do that for any other point along the beam. So if I wanted to, I could do this every foot and find what the shear moment and axial force are. Now that can be kind of a hassle, so there's better ways to do it, but this is a really good fundamental way to solve for shear and moment in a member, and it could be quickly applied to a more complex model like in RAM Elements or STAD or SAP 2000, where I'm modeling something in software. I can quickly check that the software is running correctly, which usually is more a function of, am I using the software correctly than the programming being right? All right, so I've given you an example for the free body diagram method that you guys can follow. I won't go through that in detail. The next thing I want to talk about, though, are function resources. So we'll find these types of tables here in static strengths books, structural analysis books. The Still manual has them. ACI has some cool things. If you want to go hardcore, Rourke's formulas for stress and strain are off the charts cool. Not the easiest to use, but they're good for more in-depth stuff. Um, Online calculators, I would suggest you be careful because you don't know who's writing them, you don't know how they're validated, and frankly, if someone's life or property is on the line, I would not use an online resource. Okay, so the most common point load diagrams are given here. So I have a point load in the middle of a simply supported beam. The shear is constant until the middle, and then it drops. And that shear is just half the load. So it makes sense that half of P goes here, half of P goes here. That shear travels its way through the member and comes out here. Max moment is PL over 4 at the middle. If you want to find the moment at any point along this portion here, you would do P times X, X being this dimension, divided by 2. Similarly, on the deflection, we can find the deflection anywhere along here, or we can find the max as PL cubed over 48 EI. We use the shear to design the web of a member. So in a wide flange beam, that would be the narrow vertical portion. So I quickly pulled up a hunk of aluminum wide flange. This would be the web. So the shear would be used to design this portion. Moment would be to design how big the flanges are. Okay, so in here there are tables for a cantilever with a point load. Actually, let me open up this PDF that I've given you. So this has a lot more in-depth tables. It has some for moments, for fixed ends, provides the shear and moment deflection diagrams for those, and the associated equations. Here are some tables out of the Still manual. And these are pretty extensive. Those are nice and helpful. And I don't recall if, yeah, that's all I've got in this PDF. I'm going to flatten that guy. Okay, so bottom line is for very, very many types of loading and support conditions for statically determinate structures and some indeterminate, we can have these equations that basically reduce our analysis time to a very small number. And that's what we want when we're trying to size a beam. We don't want to spend half a day analyzing one beam. We want to know the forces in it, choose one that works, and move on to the next problem. Okay, so here's an example of how to use these tables, and you can follow through on that. And once you develop more questions, then we can chat more in class when we meet next time.